So yesterday we were going to start the fourth option of how to add and how to prepare phenols. This option is probably the most important option because this uses catalysis. It has very favorable conditions, okay? And favorable conditions are normal conditions that we like. And this happens at 100 degrees Celsius. So you don't have to force the issue. Now, catalysis for inorganic catalysts, okay, it is normally done, I think, in third year, okay, in one of the inorganic topics. But this cycle here is one that is very impressive. Now, what you have is the palladium first reacts and complexes with the phosphines. Once that happens, then it can interact with the benzene ring, specifically with the halogen. Okay, so it replaces the halogen with an OH group. Okay, now this catalyst, because it's a complex, most complex salts, okay, most complexes would actually be soluble. Okay, so you would be having here a homogeneous surface. You would be having a homogeneous mixture. Okay, and that is exceptionally important. And that is exceptionally important. Okay, so keep that in mind, because at the end of the day, once you start taking a look, once you start seeing these kind of reactions, then it will be possible to start thinking of how to prepare different reactions, how to prepare different compounds, and which route you could be taking. Choosing the right route, okay? Choosing the right route is probably going to be the most important, okay? So here you have a reaction, and this will be at 100 degrees Celsius with the phosphine, palladium catalyst, and the CoOH as the nucleophile. It also works for amines. So normally we have this belief that whatever works for phenols would work for phenylamines, and this is normally true, okay? And this is normally true. That is something that you should keep in mind, that is something that you should note, because this is all normally the case, okay? And depending on what you use, you're gonna get your product, your different product. So again, keep that in mind, because at the end of the day, that will be something that is going to be very important when it comes to choosing and to preparing your compounds. Okay? So this is the mechanism. Now, with regards to the mechanism, again, we're not going to do the full mechanism, but you're going to assume that. You're going to assume a few things here. Okay? First and foremost, the palladium is going to it's going to cleave the carbon-halogen bond. The palladium can then lose the carbon-halogen bond, okay? And it can interact, and it can form a palladium hydroxyl bond, and then you're gonna form a carbon hydroxyl bond, okay, to form the phenol. Important, very, very important there. Now you might be telling me, or you might be thinking, but why is this reaction so important? Because this has decreased the energy so much, okay? The reaction here, for you, what you need to consider is that cleaving that carbon-halogen bond is not easy, okay? That is what you would need to consider. Cleaving that hydrogen-halogen bond is not easy. So if you can cleave it, or at the point that you can cleave it, then you're gonna have something that is pretty much exceptional, okay? Now, those are the preparations of phenols. Now we need to speak a little bit about the basicity or the chemistry of phenols. So phenols are basic. And they are basic means that they can obtain a proton. Okay? They are less basic than alkanols because the electron pair is tied up by resonance. Okay? So they are very slightly basic, but they're still basic. And I'm trying to emphasize that they are basic anyway, because sometimes we tend to miss that. Okay? They can still take in a proton. They are weakly basic, but if there is a strong electron donor, it can still give it to them. Okay? What will not happen though is the removal of water. What will not happen though is the removal of water. Okay? You will not be able to break the carbon-oxygen bond. Okay? You will not be able to break the carbon-oxygen bond. Now, the reason why phenols are weaker acids, okay, is an easy one. So phenols have the lone pair shared in the ring. So the lone pair is not truly available to interact with a proton, and therefore, if it's not going to be truly available to interact with the lone pair, to interact with the proton, then it's not going to take a proton that much, okay, or that easily. But phenol is a good leaving group, okay? So whenever you have phenol or a phenyl ether, consider that these are very good leaving groups, okay? You can easily have something to replace it. So you can break down ethers or phenoxide ethers, okay? So it's not a normal ether. So remember that normal ethers are very unreactive, and to break them down, you need a very strong nucleophile, like I- and HI, okay? In fact, first you protonate the ether, then you produce a good leaving group, then you can react to the reaction. Here, normally even a simple nucleophile will be able to do the trick. Okay? Again, you wouldn't normally want to break these kinds of ethers unless you are using them as protecting groups. Okay? Protecting groups, again, is something that we will be doing later on. So, phenols from ethers by Williamson synthesis. So, ethers are easily made because the phenoxide is easily produced. So you just need to use something like NaOH, produce the phenoxide, and once the phenoxide is produced, you can then follow up a SN1 or a SN2 reaction, and depending on your halogen alkane, and you'll get your ether. Okay? In fact, this is normally high yielding. 63% here means it's not been completely optimized yet, but 62% for such reactions. Phenoxide, the phenol is very cheap. The bromopropane there is very cheap, and therefore 60% is something that you don't really mind. But for phenols to form esters, then you do need a more reactive acylating agent. Carboxylic acid only will not really do the trick. Okay? Now, why? Because the lone pair that is normally going to be attacking, okay, the C double bond O, is not truly there. It's going to be shared with the ring. Now, what you then need to note is that you will have to use either acid chloride or an acid anhydride. Acid anhydrides normally are going to be good enough. Acid anhydrides normally are going to be good enough, okay? And the solvent we normally use ethanoic acid or propanoic acid or something of the sort, or ether, okay? Don't use water, because the water would then react with the acid anhydride itself. But remember, pay attention to which is going to be the most nucleophilic site on the carbon. Okay, because if you're going to have an amine group, for example, this would simply react with the acetyl hydride itself. Okay, and H2 is more nucleophilic than the OH. Okay, even if you consider amines and alcohols, amines are more basic, so more nucleophilic than the hydroxyl groups. Okay, so this is something that you would need to think about. This is something that is very important for you to know. Okay, and I'm saying this because if you forget that you need to know, if you forget that you actually need to be in a position to choose the most nucleophilic site for your reaction, then you'll start missing some important factors. Then you'll start missing some important notes. Okay, and it's not always the best idea to do that. Normally, at the point where you start missing these things, you start getting a fair few problems. Okay, normally then you start having a few problems. Okay, again, not to try and scare you off here, but these are important, and you would need to ensure that you know what's going to react where. Electrophilic aromatic substitutions. Phenols will, of course, undergo electrophilic aromatic substitutions. Okay, and the para product will be predominant because of steric hindrance, both electronic hindrance, because the OH group is going to be present and it will be pulling the electrons towards itself, but it's going to be in a position where steric hindrance is going to be predominant. In fact, the bigger the substituent group you're going to form, the more para it will go. Remember, if everything was equal, the ortho products, okay, should be at a 2:1 ratio. But the reality is that the ortho products will not be in a 2:1 ratio. Okay, the ortho products will not be in a 2:1 ratio, and therefore something else must be taking place. And therefore something else must be taking place. So always keep that in mind. So halogenation is fast. In fact, the halogenation will not actually need, a catalyst. Okay, and in fact, the halogenation, okay, will just take place without any hitches, without any problems, and the halogenation will simply be the trihalide being formed. Okay, it's very difficult to form less. Okay, if you want to form less, you would need to go to colder temperatures. Now, if you were to have something like a methyl group as well, then you might end up with monosubstitution. But please note, there's 20 degrees Celsius, 0 degrees Celsius. Okay, so the temperature is different. Cooling down the reaction, you will have a chance to actually stop it. Okay, cooling down the reaction, you will have a chance to actually stop it. Okay, maybe it's not the perfect situation, but you will have the option. And that option is sometimes what you would want. That option is sometimes what you would require. Okay. Now, the Coilbased Smith reaction, okay, this is a reaction where you are adding a COOH. Now, this is This happens because of the activation of the OH group, okay? And you will require here an AOH, H2O, and pressure. Pressure is important because the pressure in the situation, you will simply need to push the CO2 close to the phenol, okay? Remember, for any reaction to take place, you need to have collisions. If these collisions are not happening, if these collisions are not present, then the reaction will simply not take place. So here, that is what we're going to be speaking about. Here, that is the most important concept. The reactions need to be under pressure. And the mechanism, I think, it's a relatively simple one. So the mechanism, you start with the lone pair of the oxygen, okay, to attack the carbon and to form an O-, okay? And at this point, then you will have, let's see, there's a second step here. No, this is, so let's find some space and do the intermediate. So you form that compound. So to get back the resonance form, okay, to get back the delocalization, you'll simply push and remove the proton as you normally would, okay? So this is something similar to what we would normally do in an average reaction. This is very similar to what we would normally do in an average reaction. Okay, so it is a simple electrophilic aromatic substitution, but it can only happen in the ortho position because there needs to be interaction between the reagents. Okay, so that is something that you should keep in mind. Okay, that is something that you should keep in mind. So having said that, I think that this reaction, it's useful, okay? It's useful. Maybe it's not the most important reaction, but it's useful. But the Coprearrangement, where is that, the next slide? Sorry. Now, apologies. The Coprearrangement is the next one. This is the Claisen rearrangement. So if you have a methoxy group, okay, but you would end up having a C double bond C, there is bound for rearrangement here. And pay attention because this example given could prove to be a little bit tricky, to be honest. And you might tell me, why might this prove to be a little bit tricky? And the reason is simple. In this situation, okay, there is a slight possibility that you might think that you removed this carbon and put it here. That is not the case, okay? This carbon is that carbon, okay? Even though the double bond is still terminal. So let's see why. The first step that happens, okay, would be the ring attacking, as per usual, okay? The first step is always the ring attacking, okay? The first step is always the ring attacking. So the ring will attack that carbon. Therefore, this carbon would need to shift the electrons, okay? And once it shifts the electrons, then you will form a double bond O. As we said then, you will push the electrons back to the ring, form the phenoxide, and this will actually be your phenol, your product, once more. Okay? Now, very, very important types of reactions, the Claisen rearrangements, not because, or you might want to do some of these reactions for studies, okay, but not because of studies, rather the other way around. Let's say you're doing a reaction and you're getting byproducts. Why are you getting byproducts? Are you doing anything wrong? No, normally, always consider, and I'm emphasizing this, normally always consider what is happening in your reaction. Because normally there is always something that is happening in the reaction that you could change, that might be affecting your reaction itself. Okay, so let's say you prepared this phenoxide, this ether, and it changed, it equilibrated because it was under reflux. So always keep it in mind. The Coprearrangement. The Coprearrangement, okay, is something similar to the Claisen rearrangement, okay, but this happens when you have a diene, and I think it has to be a 1,5 diene, okay? Now, 1,5 diene, you have two possible structures here, okay? And you just try to avoid having the terminal alkenes, okay? So here you have two terminal alkenes, and here you have one terminal alkene. Now, this can also happen without the phenols, okay? So this is happening simply because you have a 1,5 hexadiene, okay? So anytime you have a 1,5 hexadiene, this coprearrangement can take place. And as the previous one, it's only seen in specific examples, okay? As the previous one, it's only seen in specific scenarios. So again, keep it in mind. These are not your everyday reactions, okay? But you need to know them because they are good to have in your repertoire, pretty much. They are always good to have in your repertoire. That is something that I think sometimes we miss, okay? Your repertoire of reactions should always be as rich as possible, okay? Your repertoire of reactions should always be as rich as possible. Okay, so why might this happen? So you can either have release of ring strain. Now again, to get the structure in the first place, it's not easy. Okay, it's not easy. So I don't want to tell you that that is something that's going to happen all the time. It's truly not easy. Okay, or you can have isotopes or isotopic labeling, and these isotopic labeling, at that point, you might want to try and see what's going to happen, okay? But again, isotopic labeling, in this case, for example, here, doesn't really matter. In fact, it's a full equilibrium because you still have two terminal alkenes, but in the other one, you do have a structure, okay? You do have a structure where you will literally have a situation for stability. Okay, so this is considered as the Claisen rearrangement, but it is particularly known as the Coprearrangement. So the Claisen rearrangement was this one. Okay, again, you still have a 1, 5. So 1, 2, 3, 4, 5 double bond. Okay, and just know that it is very, very possible. Now, something that I normally tell students to pay attention of or to think about is this. Here, you have an ether with two alkenes. Normally, carbonyls are going to be much more stable. So what happens? You will form the carbonyl. Okay, so you would need to keep that in mind. Stability is relative. Okay, so stability is something that not everything is as stable as each other. So that is something that you would need to know. Okay, the fact that things are not going to be all of the same stability is something that you would need to know. It's something that you would need to understand. Arrhythmias. So we spoke about phenols. Let's speak a little bit about arrhythmias. Okay, they react simply like amines. Okay, but they're gonna be a little bit less basic than the normal amine. Okay, due to the resonance form. So the lone pair is going to be trapped a little bit inside of the structure, inside of the resonance forms. But the most important thing about phenylamine is the fact that you can get, the diazonium salt. Okay, we've seen how to get the diazonium salt during our last week's lesson, okay, our last week's lecture, and that is pretty much the most important aspect of these kind of reactions. Okay, and the reason why it is hugely important is because the diazonium salts then can actually use or be used for a number of different things. Diazonium salt, if you had a primary amine and form its diazonium salt, normally this would not be stable at all. Okay? Normally that would simply be completely and utterly unstable. Okay? But in this case, simply because you have the delocalization, the positive charge can go along the ring, and it increases a little bit the stability. Maybe not to the extent that it's going to be fully stable, but it increases the stability. Okay, so again, keep that in mind. Okay, so up till now, everything we're speaking about resonance forms. So when it comes to aromatics, the most important concept would be the resonance forms. Okay, so those are simply your bread and butter. At this point, resonance forms are everything. Okay, so when you actually remove the N2, you end up with a phenyl cation. But phenyl cations aren't going to be stabilized by the ring. Okay? There will be delocalization, but phenyl cations can't really be stabilized by the ring because we can move a negative charge around, but to move the positive charge is going to be much harder. You need to break and make the bond. Okay? So the N2 elimination leads to useful substitutions, and they are going to be pretty much straightforward. So at that point, you are going to be in a position where you are going to have the reaction. And you can't do anything to try and avoid that. Not that you would want to avoid the reaction, but it's a situation where, unfortunately, or maybe fortunately, you're going to have your compound, your reaction, and it will take place. Okay? And it's very good because it will keep its position. So if you had resonance form around the ring and you have a substituted ring, okay, it would not keep the position. But the reality is that this kind of reaction will keep the position of where the amine was. Okay? This is the Sandmeyer reaction, copper catalysis, for the addition of chloro, bromo, and nitrile. Okay? You do need a catalyst here, but this reaction works relatively nicely. Okay? Please note that the temperatures are not at room temperature. So if you want to do these reactions, you cannot just tell me room temperature. Okay? These reactions are not at room temperature, therefore you cannot tell me room temperature. Again, trying to make a bit of an emphasis here, simply because these will become important later on. Okay, so normally you're used to doing these reactions all at room temperature, aren't you? 0 degrees, then go to room temperature. But to add the chloride, you need to form 60 degrees. To add the bromide, 100 degrees. Cyanide, 50 degrees. Pretty much the reason is that the N2 plus is going to be stabilized via the ring. And since the N2 plus is going to be stabilized via the ring, you're going to end up in a situation where you need energy to break that bond. Okay? You can also reductively remove the nitrogen, and this is similar to reductive elimination, okay? But here you're removing the N2 plus, and you will be doing this using H2PO2, okay? Where the phosphorus is donating the proton, releasing, okay? Releasing the nitrogen, with the phosphine then reacting with water to form H3PO3. Okay, now here you do have replaced by OH. It's replaced by H2O that would form H2O plus releasing H plus. Okay, so you would form eventually now. Why might you want to do something like this? Okay, you can either try to prepare arene diazonium salts to change a substituent, okay, or to add substituents. And normally, you would want, let's say, you have I think it was in a couple of years ago, BR and I. So let's change it. So let's say you need to think about making these two compounds. 1 and 2. Because you have the iodine, and the iodine can only be added via the diazonium salt, okay? Then you need to know where to add the NO2, where to reduce it to NH2, where to add the bromine, where to add the I, okay? We'll be working a few of these examples in future lectures, okay? But it will be super important, and I'm trying to emphasize this because this would be hugely important in knowing exactly when to use what, okay? When to use the nitro, when you use the amine. Remember, you can use the nitro and the amine to actually choose and to actually say, I want the reaction to go on that carbon. I want the reaction to go on that carbon. Okay? And we can actually control the reaction. Okay? Or you can also activate a site. So for example, for the iodine doesn't really add, or for phenol, the OH doesn't really add. So you can activate the site by adding an nitro group. From the nitro group, you form the amine. From the amine, from the diazonium salt you add the nucleophile. But again, for now, I would like to focus mostly on how to do these reactions and how to eventually get in a position where we can, or where you can, because I think that's more important, do these reactions yourselves. Okay, so diazonium salts, you're gonna be using them, and I'm referring you as in your exams, in your tutorial sheets, you will be using these to actually get in a position to see how everything works. Okay, it's not that everything is gonna work brilliantly, especially in the beginning, but things will work. Okay, so first and foremost, let's stop the recording here.